One point of emphasis in lab this semester is going to be error and understanding error. So we've got several things we're going to go through in the pre-lab, well, in the lab exercise for the first week, which we missed because of weather. And we got a set of 15 problems you're going to do. Most of these are fairly straightforward. It comes down to understanding some notation at the end of the day, and we'll work on understanding that notation. So problem 1 is the first place where we see this cropping up. There's a notation some of you have seen, some of you may have seen, but let's get to it. Okay, so here, this right here, the mean is defined as 1 over n, the sum from 1 to n of x sub I. What does that mean? Well, we have down here a set of numbers, x1, x2, x3. So we're going to take these, add them together, and divide by 3. That's all this equation up here is actually telling us to do. All right, it's pretty straightforward when you look at it, and not something that you really have to work hard at doing. So the first problem, that's kind of a gimme. Okay, the second problem. The second problem is the standard deviation or standard error as we calculate it, and this is the n-1 version. There are several different ways of calculating this, or several different versions of standard error. This is the one we're going to go with today. So S sub x is the square root of 1 over n minus 1, the sum of 1 to n of x sub I minus the mean squared. All right, so it's important that you note that we're squaring the difference between the value and the mean. Where does that come into play? Well, in a lot of places, this is one of the ways that we look at error, basically. There are other models for looking at error, but this is the standard one that we use for things that we presume are a Gaussian distribution. And usually, when you're talking about measurement error, where you're going to repeat the measurement over and over and over again, there is some Gaussian distribution of that error or that result around a mean. And 68% of the data is within 1 standard deviation, 95% should be within 2, and 99% should be within 3. We sometimes call these confidence levels, right? We're confident at 95% level that something is within 2 standard deviations of some central value. If we look at 2 random samples, then 40% chance that both will be within 1 standard deviation, which would make this up here a bit of an underestimate of the standard deviation. If we have 3, there's still a 33% chance that all 3 of them are within 1 standard deviation. So again, this on small numbers is just an estimate. On a small sample size, it's just an estimate. But I want you to go through it. I want you to calculate the standard deviation for these 3 numbers. It's a pretty straightforward thing to do. You got to calculate the mean first, and then you've got to go through this formula: the first number minus the mean squared, plus the second number minus the mean squared, plus the third number minus the mean squared, and then divide all that by 1 over n minus 1, so n is 3, so that's 1 over 2, and then take the square root. The third problem is another way to just get a quick and dirty estimate of the standard deviation or standard error of a set of measurements, and that's just take the maximum value, subtract the minimum value, and divide by 4. All this is doing is presuming that the maximum and the minimum are somewhere out around 3 standard deviations, and if they are and you divide by 4, you're getting in the neighborhood of you're getting in the neighborhood of the size of the standard deviation, assuming these are out near the edge of the 1-2 point. So again, just another quick and dirty estimate, not the kind of thing that you would want to write a scientific paper based on, but it is something you might use at some point when you're trying just to work through something on a napkin sitting around having coffee, which is when you actually do real science. All right. So Number 4 is pretty straightforward. Often we state the error on something or the accuracy of something as a percentage. That is typically meant to be one standard deviation. So if we say the scale has a 5.06 accuracy, and when we measure 50.08 grams, what's the standard deviation in grams? Well, you just multiply 50.8 times 0.0506. Right? That one's pretty straightforward. This semester, we're putting the absolute value signs around, and I actually should have, I didn't, but I probably should have made these go all the way, right? We're talking about the magnitude of this. We're not worried about anything other than magnitude. So the measured value minus expected divided by expected times 100%, that's going to be our standard error. And so calculate that. That's going to be our percent error. So calculate that from these numbers. All right, with problem 6, we're switching gears a little bit. Now we're looking at how to propagate the standard error through from a measurement we make to a quantity we calculate. So this is a straightforward example. If the error on our measurement of mass here is 0.34 kilograms, then weight equals mass times acceleration of gravity is at the end of the story. Right? Because that means, because this has some spread on it, or some potential error on it, that means our weight has some potential error on it. And to calculate that, we can look at, well, what weight plus or minus its error equals mass plus or minus its error times g. Well, if you take into account weight is mass times g, you can pull that out of here. You're left with the error on the weight is acceleration of gravity times the error on the mass. That's fairly straightforward way to think about it. We're going to go a step further in the next problem. What do we do when we have two variables that are moving? All right, and so we got mass and we've got height. We are presuming here that there is no correlation between mass and height. That if we look at the autocorrelation between the errors on these two, that it is in fact 0. You can imagine scenarios in which it's not quite 0. For instance, if we're using a ruler to measure the height, and we're using a spring scale to measure the mass, well, the length of the ruler and the length of the spring depend upon temperature in the room. When it's hotter, they're a little bit longer. When it's colder, they're a little bit shorter. So in fact, underlying physics of temperature can change these measurements. Now the reality is the correlation coefficient between these two is itsy bitsy, because we're talking microns difference on a meter. We're talking microns, well, we're probably talking nanometer differences on a couple centimeters of spring. And so that correlation between the two is so tiny that we can throw it out almost all the time. There are times, and if you decide to become a high energy physicist, you will have to study the correlation between errors in different parts of your system, but those are large complex systems with lots of data. That's not what we're talking about here. So if we look at what the error on the spread on potential energy due to a spread on mass and a spread on height on potential energy is mass times acceleration of gravity on height, then what we find is that it's the central value mgh times the square root of sigma m over m squared plus sigma h over h squared. So you'll see over and over again that when we're looking at error, the squares tend to add, and we take the square root. And if you look at this, sigma m over m is the fractional error, and sigma h over h is the fractional error. So this is the standard error in potential energy for the data given above. All right. And of course, sigma m is, well, you got sigma m, you got sigma h, you've got mass, you've got height, you got everything you need to calculate that. We're going to look at a different equation and go a step further. So Q equals mc delta t. Again, we have one variable m, we have c a constant, and we have delta t, the other variable. We have the errors on mass and temperature. And so we're using the same form of the equation here. It'll be MC delta t square roots of sigma m over m squared plus sigma t over delta t squared, right? All right. So we're going to calculate the sigma q, the error on the heat measurement, and we're going to convert that to a percent by just saying the percent error is sigma q over q times 100%. Right? Pretty, again, pretty straightforward. All right, problem 9. We often talk about confidence levels. I mentioned this before. Suppose your systolic blood pressure is 125 millimeters of mercury with a standard error of 5.3 millimeters of mercury. What is 95% confidence level on your true maximum blood pressure? Well, we're 95% confident that the maximum is no more than 125 plus 2 times 5.3, because 95% is 2 standard deviations. We multiply the standard deviation by 2, add it to the mean. That's our 95% confidence level on the maximum. Now, here, depending on how you're trying to control your blood pressure, you might actually be over and not know it because of your confidence level on your blood pressure. All right, number 10, and then after number 10, I'll pause, I'll stop this version, and we'll discuss problems 11 through 15 in a separate video. All right, number 10. And number 10, we often talk about errors as full width, half maximum, and if you have Dr. Smithhart for a class, you'll probably run into this in one of his analytics or quant classes. The reason is, this is much easier to measure on a piece of graph paper. So if you have a graph of a distribution, it's pretty easy to say, okay, I'm going to find the central mean. I'm going to go to find out where that hits the axis over here. I'm going to go to half that, and I'm going to come across and find out how wide is this distribution at half of the height of the central value. All right, so full width at half the maximum. Well, when you look at this in terms of the standard deviation, right, this is 2.355 standard deviations. The reason we look at this is it's much easier to do than figure out exactly where you should have 2 sigma and measure that off, right? Much easier to do than measuring sigma on a graph because you're dealing with strictly 1/2 of the maximum. All right, that's it for problems 1 through 10. Come back for problems 11 through 15.